Modeling with exponential and logarithmic functions. As you can see with this lesson, there are lots of state standards that we touch on for this lesson. And for your success criteria, you need to be able to use a common ratio to determine whether data can be represented by an exponential function. You need to be able to write an exponential function using 2 points, and you need to be able to use technology to find exponential models and logarithmic models for sets of data. Example 1, using differences or ratios to identify functions. So number 1 says determine the type of function represented by the table. Okay, so here's something to remember. So your first differences of linear functions are constant. The second differences of quadratic functions are constant. The third differences are constant for a cubic function, and so on. Okay, so that's just something to remember. So basically, if you're adding or subtracting to get to the next term, and that's a constant number, then that's where the linear quadratic terms come in. That's where you can determine whether it's linear or quadratic. All right, so if we're looking at a table and we want to determine if it's a exponential function, which is what we've been working on, exponential and logarithmic functions, it says that we're going to have to use the differences or ratios to identify this. So to determine whether an exponential function can be used to model the data, the output, the y values, remember your output is your y values, must be multiplied by a common factor. So that's what we're going to look for. Is it multiplied by a common factor, or does it have a constant number that's been added or subtracted to the next number? All right, so let's look at the y values. That's your output. Okay, so 0.5 to 1. If it's a decimal or a fraction, sometimes it's a little harder to see. 1 to 2, it's either add 1 or multiply by 2. How do you get from 2 to 4? Multiply by 2. 2 times 2 is 4. 4 times 2 is 8. 2 times 8 is 16, and so on. So you can see here there is a common theme. So we're going to say times 2, times 2, times 2, times 2. Now, from 1 to 2, 1 times 2 is 2. And what about 1/2? 1/2 times 2 is 1 as well. Okay, so sometimes once you find that pattern, or you find that common ratio in this case, that you can see that that's the case. So this is multiplied by 2 each time. So because that is the same number, that would be your common ratio. And so we can say as x increases by 1, you can see x increases by 1 each time. The y value is multiplied by 2 each time. So the common ratio is 2, and that means that this data represents an exponential function. Okay, let's look at part B. All right, if we look at the x values, we can see that these are evenly spaced. Your x values are spaced equally by 2. We can look to see if we have a common ratio. Is there something that we multiply to get to the next number? From -1 to 8, 8 to 7, that decreases. And this one decreases again, and then it increases here. So there is no common ratio to get from one to the next. So that means we have to look at the finite definition. So let's look at the differences. So up here, you remember, if the first differences are constant, it would be linear. If the second differences are constant, it would be quadratic, and so on. All right, so let's look from -1 to 8. That is a difference of +9. 8 to 7 is -1. 7 to 2 is -5. 2 to -1, that's -3. -1 to 4 is +5. 4 to 23 is +19. So we can see it's not linear because those first differences are not constant. All right, so let's check the second differences. That means we got to look at 9 to -1. From 9 to -1, it's going down 10, so -10. -1 to -5 is -4. -5 to -3. All right, so -5 is smaller than -3, so that's actually a +2. -3 to 5, that's an increase of 8. And from 5 to 19, that's an increase of 14. So you can see that these differences are not constant as well. So that means it's not quadratic. So let's go one more time. So if we go from -10 to -4, remember -10 is smaller than -4, so that's an increase of 6. -4 to 2, that's also an increase of 6. So from 2 to 8, that's an increase of 6. And from 8 to 14, that is an increase of 6. So you can see in this case, these are now constant. So this is my first difference, my second difference, and my third difference. Because it's my third difference, that means this data represents a cubic function. So this one would be a cubic function. And we said this one up here was exponential. So just to look at the differences, the first one, A part, you multiplied by 2. So that one had a constant factor, a factor that we multiplied by 2 to get to the next term. This one had on the third round, we call it a common difference, but this case it was a common sum. So we added 6 on the third round, which means that would be a cubic. If these were all the same on the first round, it would be linear. If they were the same on the second round, it would be quadratic, but it wasn't. It took us 3 rounds to get to the common difference, so that means this function is cubic. Example 2, writing an exponential function using 2 points. Write an exponential function in the form y equals ab raised to the x power, whose graph passes through 1, 6, and 354. All right, so remember every ordered pair is an x and a y value. So this one is x and y, and this one is x and y. So let's go ahead and substitute those values in for my 2 equations. So for the first point, x is 1, y is 6. So I'm going to put 6 equals, and I'm using this equation here, and I'm just substituting my x and my y. So that does not look like an x or a y. Let's see. I'm just going to let you know that this is your x, this is your y. I'm not going to try to write that there. There's just not enough room. So we're going to have a, b, raised to the x power. In this case, x is 1. All right, we're going to do the same thing with the second point. So 3 is my x, 54 is my y. So I'm going to put 54 equals a, b, and this time it's raised to the third power. I just do not write well on the computer screen. I'm sorry about that. Let's see if I can do a little bit better. A, b to the third power. All right. Now I want to solve one of these for a so I can substitute it in. So the first equation is a little simpler. So let's say I'm going to move over here. 6 equals a, b to the first power. If I want to solve for a, it means I get a by itself. So I'm going to divide both sides by b to the first. That's going to cancel. A equals 6 over b. So anything to the first power, you don't have to write that exponent. You can just assume that it's a 1 when there's nothing written there. All right, so now I can use this to substitute in equation 2 for a. So I'm going to have 54 equals, a is 6 over b, or b to the first power, times b cubed. So all I did was substitute for a what we solved for here. All right, so if this is b to the first, 3 minus 1 is b squared. So this is 54 equals 6b squared. So all I did was simplify. Now I can divide by 6. 54 divided by 6 is 9. And then if I take the square root of both sides, b equals plus or minus 3. So negative 3 is not going to make sense because b has to be positive to be exponential. So that's the little reminder over here. By definition, an exponential function, b must be positive. All right, so we're going to just forget about the negative square root and get b equals 3. So once we do that, we can plug b back in to find a. All right, so we know up here 6 over b equals a. So let's do 6 over 3 because we just found that b equals 3 is a. 6 divided by 3 is 2. So a equals 2. All right, now we're still trying to write an exponential function, which is this form right here. So we're going to say y equals, now we know a is 2, b is 3, and this is an exponential function that will work for any point, but we know that these 2 points given go through this exponential equation. All right, so we use 2 points to write an exponential function, but it says consider similar problems. 2 points can determine an exponential curve. What other types of functions can be determined by 2 points? So we also learned to write a linear and quadratic functions using 2 points. You could also do that with many other functions as well. Example 3, finding an exponential model. The table shows the number y in thousands of people who visit Machu Picchu X years after 1990. Write a function that models the data. All right, so the first thing you should do is look at a scatter plot, put the points on a scatter plot and look at it so you can determine if this is best fitted by an exponential model. All right, so you could just take these and plug them into your calculator. Here's a graph that's already been done. You can see the scatter plot does represent an exponential model. It is more curved than straight. If it were straight, it would be linear. If it was a U-shaped graph, it would be quadratic. Okay, so this does look like an exponential model. So we're going to choose a couple points. Let's choose 0, 1, 50. And 20 and 700. Those are easy points to calculate. So we're going to do the same thing we did a minute ago. We're going to put these in our function. So we have y equals 150 equals a, b to the 0 power. And then we're going to have 700 equals a, b to the 20th power. Now, we're going to solve for a and b, and then that will give us our exponential model. So the first one, b to the 0 power, is 1. Anything to the 0 power is 1. So this already tells us that a equals 150. So I can plug that in. So 700 equals 150 times b to the 20th power, divide by 150. So 700 divided by 150 equals b to the 20th power. So I need to take the 20th root of that. All right, so let's see what b equals. So let's pull up our calculator. All right, so we know that under math there is the square root, cube root button, and x root button. So 20th root, we're going to have to put in 20 and go to math and down to x root. So putting in the 21st means the root is that power. And then I've got to put parentheses because I'm going to do 700 divided by 150, and all of that should be under the radical. And that's going to give us about 1.08. So 1.08. So that means our equation, y equals a is 150, b is 1.08 to the x power. So that would be our exponential model using 2 points.